If you're a technical engineer who's considering getting into programming, this video is for you. We're going to cover language choice, not only in the context of engineering, but also in the long-term versatility and the options it gives you outside of engineering. We'll look at the basic types of programming languages, the main players, and some of their pros and cons. I'm really aiming to give you a holistic view of what is the best choice long-term, as well as obviously my opinion on where to start. Hi everyone, welcome back to the channel. If you're wondering about me, I'm a professional aerospace engineer who specializes in using AI for aerodynamics, and I'm here to help demystify new technologies and level up your engineering career. Technical engineers across disciplines and across countries tend to use a lot of the same tools. Simulation and post-processing tools, as well as general number crunching, all have their main established players. Streamlining inputs into these programs, post-processing results, and general manipulation of data is a lot of what modern engineering roles are. It's incredibly useful to add programming to your arsenal of skills to help in any of the following common use cases. Automation of reporting, tool sets to replace, for example, large spreadsheets, post-processing outputs from existing tools, the massive ramp of AI technologies. By the way, I'm also doing a series on getting started in AI for engineers. And finally, simulation. Let's look at how programming languages are broadly categorized. The first main categories are compiled versus interpreted languages. In a compiled language, a program called a compiler translates your code into machine code with a few extra steps in between, and then every time you run that, you're just running the binary executable. This is what's happening when you double-click on a .exe file. In an interpreted language, you run your file, and a program called an interpreter literally translates each line of code as it executes it and executes it on the spot. The main reason these are important categories is that compiled languages are much faster to run, and we'll explore that later, but interpreted languages are much easier to read and much quicker to write. Next, there are high-level versus low-level languages. In a high-level language, you're interacting much more with your hardware. In this C++ program on the right, on line 7, we create an array of numbers, but we have to declare ahead of time how large that array will be. This is because when you run it, your computer digs into your memory and literally finds a slot in memory that is large enough for all that information to fit into. In a high-level language like Python on the left, you just say, make this list, and your computer goes and does it. You can add stuff to the array or subtract it, and the language takes care of all the underlying memory allocations without you even knowing. These two programs here do exactly the same thing, but look at how much simpler the Python code is. Finally, there are static and dynamically typed languages. In C++ again here on the right, we have told the compiler that the variable called test will be an integer. This is so it knows how much memory it needs to allocate. However, if you change your mind later and decide you want it to be a string, this will cause an error. Once you've declared a type, you can't change it. This does have advantages, as it stops you making many mistakes. In Python again, the variable myText doesn't have a declared type, but the interpreter infers from the syntax that it's a string of characters. I can then decide I want it to be an integer, and there won't be any issue reassigning it in memory. Its type is dynamic, and it's all taken care of by the interpreter. Let's have a look at some of the main languages that are relevant, and throw MATLAB in there for context with engineering. I've grayed out Java because it's the only one on the list that I don't know myself. All my metrics for it are based on research I've carried out. I'm experienced and proficient in all the others. Starting with C and C++, they are extremely performant. They are the most performant languages in the world because of their low level, static typing, and what's called zero overhead abstraction, which you don't need to worry about now. The trade-off is that they are not easy to learn and are not suitable in my opinion as a beginner language. We'll talk more about the long-term roadmap later. It has some libraries, but honestly, if you come from something higher level, you'd be amazed and disappointed at how difficult it is to do something like read in a spreadsheet or open a window. They have been around for decades and they are used in every area of tech, so there is a strong community to learn from. From my experience too, the people who will help you learn these languages are some of the smartest programmers in the world. Its applicability to engineering is massive because when it comes to performance, there is nothing better. This is why any major simulation software will do the heavy maths in these languages. Anything else is unacceptably slow by comparison. With Python, you immediately sacrifice speed. If you have a few nested loops of things running, for example operating on every row and every cell of an array of data, it can literally be 100 to 1,000 times slower than C++. That may sound bad, But we're living in an era in which computers are so fast that for any day-to-day small to medium-sized task, we as humans could barely tell the difference. It's only when you get into major high-performance computing that the lower languages come in. It's extremely simple to read and write, which means the development time is much faster than many other languages. It's quicker to just get something up and running in Python than in any other language I know. A lot of priorities in tech companies now are in development time rather than runtime. It is unmatched in libraries, and we'll discuss them in the next slide, and the Python community is gigantic. You will not come across an issue for many years that someone hasn't already faced and asked online. Because of the wide array of libraries available and the development speed, it's very applicable to engineering, and importantly, it's extremely transferable in case you don't want to stay in engineering long term. Again, we'll cover this later. JavaScript is a mixed bag. Obviously, being for web development, its community is also gigantic. But it really is the language of the web, so it's not optimal for scientific computing or automation. Java is another language designed to be simple. It's very popular and has the benefit that anything you write in Java will also work across any device and operating system. However, it is, in my very biased opinion, a jack of all trades and master of none, though please do take that with a pinch of salt because I don't use it myself. Finally, as an engineer, why not just learn MATLAB? Well, it has its pros and cons like the rest of them. It's slow, it's not actually that simple, it's not free, the community is much smaller, and while it's extremely valuable in engineering teams, it doesn't leave you much opportunity to move on if you decide to leave engineering. Looking back to our immediate use cases then, in 4 out of the 5 tasks here, Python fits the build perfectly. There's only simulation for which it wouldn't be a serious option. Simulation programs are massive. Certainly not something you should be aiming at as a learning project for the first couple of years. So let's talk about libraries, possibly Python's greatest strength. These are examples of the most widely applicable libraries to engineering. NumPy is a numerical library with extremely well optimized linear algebra capabilities and the option of working with huge arrays of data. Pandas is something that, even if you learn nothing else, would be useful for most engineers. Pandas is roughly a scripted version of spreadsheet logic. We've all had one of these going at some point. A messy spreadsheet with tons of macros loaded with plugins and formula dependencies you can't even track anymore. These can be completely replaced by pandas with clean functions and if statements, a linear trackable workflow with printouts available at any stage. The ability to perform loops on data and also export it straight into NumPy arrays for other purposes are both useful features as well. TensorFlow and PyTorch are the world's leading AI and machine learning frameworks. Very simple setup in Python, and the libraries go deep into your hardware and actually run the heavy maths in C++, even running them on your GPU. They are some of the best optimized libraries of any kind that I've ever used, and nothing else comes close for machine learning. Finally, if we're going to replace MATLAB and Excel, we need plotting functions. Matplotlib and Seaborn let you create very clean and versatile plots. Matplotlib also lets you plot in 3D. If you watch my other video on getting started with AI, you will see Matplotlib graphs in there. So what about the long term? What if you don't want to stay in engineering forever and you want to set yourself up for a strong future in the job market? Python is used in all these applications, and if you're in any slightly numerical role, you still have the ability to automate anything, such as the pulling of reports and creating graphs in one click that you can then dump into a PowerPoint. If you do stay in engineering, eventually you'll run out of performance. It always happens. When you do, you'll have enough experience to make the transfer to C++ not that bad. If you decide later that you want to learn something else, your Python experience will be a big help, especially learning another high-level language. When I learned C++ after quite a lot of Python experience, it took me months to get good at it, but honestly, I learned JavaScript basically in a weekend, other than a few language-specific features. Once you know one programming language, you realize that changing languages is nowhere near as difficult as learning how to program. Once you understand the fundamental building blocks of logic that programming languages consist of, you'll see that learning a new language is just a change of syntax a lot of the time. Though it is always easier to go from a low-level language to a high-level language than the other way around, and it's always quite simple to go parallel. Anyway, I hope that helped. Feel free to leave a comment asking any questions. If you found this video valuable, a like would really help the channel out. Subscribe if you want to see the rest of the series, and thank you for watching.